Yeah, thank you very much. Hi, everyone. Thank you for attending my talk. So my talk is about efficient quantum circuit and applications of the mixed-Schur transform. And I guess it's a good thing for me that Dimitri gave a very nice talk introducing the background in representation theory. So I guess I'll have less work to do, hopefully. Um, so what is this? So as Dimitri said, the mixed-Schur transform is a generalization of the so-called Schur transform. And this Schur transform was introduced and studied in the context of quantum information almost 20 years ago by Bacon, Chuang, and Harrow. So for background, I'll first introduce to you the original Schur transform. So let's look at the simplest example. So we know that the 2-qubit Hilbert space has a spin couple bases spanned by the singlet state and the 3 triplet states. So the unitary that maps from the computational basis states to this couple basis states is indeed the simplest example of the Schur transform. So the spectral properties of these couple basis state is that in this basis, the permutation operators of the qubits diagonal, and the tensor product of any 2x2 unitary with itself is block diagonal. And this is no coincidence. This comes from facts in representation theory. So the qubit permutations indeed form a representation of the symmetric group S2. And the U tensor N is a tensor representation of the qubit unitary group U2. And the reason that they're both block diagonal in this basis is because these two representations commute. So more generally, we can consider an n-fold tensor representation of a qubit unitary group in which a d by d unitary matrix is mapped into from U to U tensor n. And the Schur transform is defined to be the change of basis that block diagonalizes this U tensor n. So now each block corresponds to an irreducible representation of the unitary group, and each block further has a tensor product structure where in the first component corresponds to a in the first component the group element acts irreducibly, and on the second component the group element acts trivially. And I'll refer to the first component as the irrep space and the second component as the multiplicity space. So generalizing the example in the previous slide, this Schur transform also block diagonalizes the permutations of qubits, except now within each block, the irrep space and the multiplicity space are swapped. So here are the examples of the block structure in a small example. So what Bacon, Chuang, and Harrow did was they developed the first efficient quantum circuit for this Schur transform. And this transform is great because it made many protocols in quantum information efficient. So this talk is about this mixed tensor representation. So now in addition to the U tensor N, we have now M copies of the dual representation, which for the case of the unitary group is the complex conjugate of U bar. And now our goal is still to block diagonalize this representation. So as an example, in this case, when n is equal to 2, m equals 1, d equals 3, we're hoping to go into a basis such that this U tensor and tensor U bar looks like this. So just to contrast with the original Schur transform, when n is equal to 3 and m equals 0, the block structure could be in general very different. So why are we interested in this mixed tensor representation? So the main motivation of my work comes from the many recent papers studying so-called unitary equivariant quantum channels. So these channels have the following property. If you apply any unitary U on all the input qubits and then apply the channel, then that's the same as applying the channel and then the same unitary on all the output qubits. It turns out that these channels are interesting because for many figures of merit in quantum information, such as entanglement fidelity, we can restrict our consideration to these unitary equivalent channels. And the mixed tensor representation shows up when we look at the choice state representation of channels. And it can be shown that the choice state of these channels must commute with this mixed tensor representation. So these channels have many applications that I listed here in recent work. And the simplest example to explain is the so-called quantum majority vote, in which we want to output the majority quantum state without knowing what basis the states are in. So I think the question that's underexplored in these works is how to actually efficiently implement the channels. And the most common scenario that I've seen in these works is usually we know how the channel will look like in the Schur basis, and we want to implement it. So the motivation is, with the mixed Schur transform, hopefully we can bring the state in the Schur basis back to the computational basis. And another motivation not directly related to quantum information is that this mixed tensor representation turns out to be the symmetries of several interesting Hamiltonians in supersymmetric quantum mechanics and some condensed matter models that are believed to be toy models of some types of high temperature superconductors. Yeah, so the main result of my work is to show that this transform can be done with essentially linear complexity in the number of qubits. And yeah, this is also achieved in 2 independent works that are in this session. And I think the second paper approaches differently. And they, in the paper, it seems they also only consider when m is equal to 1. So let me now describe the construction in more details. So the goal is to implement the following map as an isometry. Excuse me. Yeah, so the input, if the input of the isometry is a linear combination of computational basis states, where the coefficients are the matrix entries of the mixed Schur transform, then we want to map the state into a bit string that basically tells us the original state would have been this state in the Schur basis. So we need now to come up with an encoding scheme to encode this Schur basis. So for this, in the original Schur transform, this was done by looking at the basically combinatorial objects called the Young diagrams. And the reason is because the U tensor n representation is a polynomial representation of the unitary group. And a polynomial representation means that the matrix entries of representation are polynomials in terms of the matrix entries of U. And we know that polynomial, it turns out that polynomial EREPs can be labeled by Young diagrams. So for us, this mixed tensor representation is in general a rational representation. And what that means is that the matrix entries are rational functions of the matrix entries of U, as can be seen from the example of U bar, which is equal to the transpose of the inverse. So these rational EREPs can be labeled by a slight generalization of the Young diagrams, which are called staircases. And for the purposes of this talk, we can just simply think of these as a pair of Young diagram, which satisfies some some extra properties. So for the EREP space register Q gamma, we can also quite easily label this by something called the Galvin patterns. So these are just triangular arrays of integers, such that the first row corresponds to the EREP label. So the more non-trivial part is to label the multiplicity space register. So for this, we need the mixed Schur duality. So this duality is a generalization of the well-known Schur duality, and is about the commutant of the mixed tensor representation. So for example, let's look at this simple case, when n is equal to 3 and m is equal to 2. So what operates to commute with this mixed tensor representation? So clearly the permutations of the first 3 qubits or the last 2 qubits commute with this representation. The new element now in the mixed Schur wild duality is the EPR state projectors. So for example, the EPR state projector on 3 and 4, qubits 3 and 4, commute with U and U bar, as you can easily verify. So if we look at the algebra generated by these swap and EPR state projectors, you get something called the partially transfer permutation algebra. And this algebra is the representation of the diagrammatic Wald-Brouwer algebra, and which I won't go into the details of this, but these algebra are generated by the diagrams like representing the permutation and the EPR projectors. So the theorem is that the PTP algebra A and the mixed tensor representation algebra are the commutant of each other. So now we have a one-to-one correspondence between the multiplicity space register of the unitary group and the ERAP space register of the PTP algebra. So what we can do now is we can use the labeling scheme for the ERAP space of the PTP algebra, and we do this via the so-called Bradley diagram. So this diagram is a graph that represents basically the relations between the ERAPs of the PTP algebra as we increase the number of qubits. So when n and m are equal to 0, the only ERAP is the trivial ERAP, which is labeled by 2 empty Young diagrams. So the statement is that this ERAP space of the PTP algebra has a basis that can be labeled by paths in this Bradley diagram. So in particular, if we look at an ERAP gamma that's labeled by the Young diagram to the rightmost of the diagram, of the Bradley diagram, then we can just trace back to the root, and that enumerates all the basis elements. So how do we get this path when we implement it on a quantum computer? So the claim is that these paths arise naturally when you try to implement the mixed Schur transform as a sequence of so-called Clebsch-Gordan transforms. So Clebsch-Gordan transform is a primitive that allows us to combine 2 ERAPs into a direct sum of ERAPs. And in our case, one of the input ERAPs is either the defining representation U or the dual representation U bar. So now what we do is we implement a sequence of Clebsch-Gordan transforms, and then we keep track of all the ERAPs that appear along the way. And then these ERAPs form exactly a path in the Bradley diagram. And this gives us a multiplicity register labeling. So now the last piece of the construction is to implement these Clebsch-Gordan transforms. So naively, we can do this quite straightforwardly with complexity exponential in D. The non-trivial and most technical part of the construction is to bring this down to D to the 4th, which I unfortunately don't have time to go into the explanation. So now combining everything together, we can see that the gate complexity is linear in the number of qubits times D to the 4th. Okay, so now I'll talk a little bit about applications. So as stated in the motivation part, we want to implement unitary equivalent channels. And the common setting that I see in this literature is that we essentially can prepare the choice state efficiently in the Schur basis, and we want to implement the channel. So now with the mixed Schur transform, we can bring the choice state to the computational basis. But now how do we implement the channels? So of course, in general, for general channels, we cannot do this due to the no programming theorem. And so the hope is, to exploit the unitary equivariance of the channels and try to do better. So indeed, when the number of input qubits is small, then in the paper, I show that we can do this deterministically by performing the shown POVM on one half of the choice state and the input state. And when the input number of input qubits is a constant, essentially the probability, this can be generalized and give rise to a probability that is exponentially in M. So it looks quite unsatisfactory. But the point is, so when M is equal to 2, for example, this would give you a probability of 1/2. But the point is, this is independent of D, so this is better than the naive probability of D minus M that you would have got by using just the naive approach. And for this setting where the number of input qubits is small, the potential applications is in the task of state cloning and gate replication. In the paper, I also give some other implementations based on shadow tomography and the block encoding framework. It's not really like a full implementation of the channel, but the observation is that in certain in quite a few applications, it might suffice for us to just being able to measure expectation values on the output state. And the observation that this is exactly what shadow tomography allows us to do. And there are shadow tomography protocols that you can do with just access to the choice state of the channel. So for the last application that I'm talking about in this talk, so the last application is not related to unitary equivariant channels. So it's about an extension of a computational model called the permutational quantum computing, or PQC. So this model was introduced by Jordan in 2009, and it looks like the following. So you first prepare a state in the Schur basis, then you permute the qubits, and then perform a measurement in the Schur basis. So this model is interesting because, as shown in Jordan's paper, it has some it draws inspirations from topological quantum computing, and it can be used to model interesting problems in theoretical physics. And at the time, it was conjectured that this model is not classically simulable, and the reason was because this model allows us to estimate the ERAP entries of the symmetric group, while at the time there was no classical algorithm known for this task. Unfortunately, in 2018, this conjecture was shown to be false. So now, given that we have this mixture transform, the natural question is to generalize this to the mixture case. So now the naive thing that we could do is we can prepare the state in the mixture basis and then measure in the mixture basis at the end. So what do we do with the permutation? So we cannot naively replace the permutation by a partially transposed permutation because these are not physical. A way to get around this is to instead, if we look at a suitable linear combination of partially transposed permutations, then we have a Hamiltonian. And then if we look at the Hamiltonian evolution of this, we still have some operator that commutes with the mixed tensor representation. And now we replace the permutation by a Hamiltonian evolution. So this answer was actually introduced and used in the regular Schur case in this work by Zhang et al. In the context of variational algorithms. So is this new partially transposed PQC classical? These Hamiltonians that we were doing evolution of, as I mentioned earlier in the talk, correspond to interesting Hamiltonians in condensed matter physics. So I think the answer is probably no. And if so, it would be interesting to see what interesting physical information we can extract from the ERAP entries that we can extract efficiently with the mixture transform. Yeah. So for open questions, I think it would be interesting to find application. Yes. of this transform outside of unitary equivalent channels, and I list here some, I think, potential places that we might look at. And because of the mixture of wide duality, this transform is actually also block diagonalizing the Wall-Brouwer algebra representation. So to my knowledge, this is the first representation that, first transform that block diagonalizes an algebra representation in quantum. So I think it would be interesting to see what algebra-related transform can do in quantum information. And I listed here some relevant algebras. Thank you.
Please come to the center if you have questions.
Hi.
Hi, thanks for the wonderful talk. So I'm wondering what's known about these types of transforms with subgroups of the unitary group, because there the commutant relationship isn't, the commutant should be bigger, I suppose. Like even if you just started with the orthogonal group,
Yeah.
or like mixed orthogonal groups, do you know anything about these transforms?
Oh yeah, so I don't think there's any construction written down for example, block diagonalizing the orthogonal group, for example. But I think the framework here in terms of doing Galvin-Zetlin basis, I think should be generalizable to those cases. And yeah, and there are well-known version of Schur dualities for those subgroups. So I think it should be possible.
What about non-compact groups?
Yeah, I don't know. As yeah.
Any other questions? Oh, there's a question there at the back. Would you come there to the microphone?
Hello. Yeah, in your open questions, you are listing temporal leap as one of the examples of an algebras that might be interesting to block diagonalize. Is there any nice relationship between the Volt-Brouwer and temporal leap?
Is there any what? Sorry.
A nice relationship between the Volt-Brouwer algebra and temporal leap algebra. Do you know of it, or
is there like connection between?
Yeah.
Oh yeah. So the temporally leap algebra is a sub algebra of the full Brouwer algebra, and yeah, the Wald-Brouwer algebra is also a sub algebra of it. And I think I've seen papers studying Galvin-Zetlin basis for the temporally leap algebra. So I am hopeful that it's also doable for it.
Thank you.
Yeah.
All right. If there are no more questions, then let's thank the speaker again.
Thank you.